Fine. So we had also seen that it is not only these real life systems, but whole solar system is actually chaotic. Why? Can anyone say why? Why whole solar system I am telling it as chaotic? Like you cannot predict. So you can see like the motion of the Pluto moon is also chaotic due to particularly its shape, how it is. It's kind of an ellipsoid. You cannot predict. Like now the solar system is almost going in such a slow rate that we are able to predict that yes, Earth will complete its revolution in 365 days. And yes, we can see it. We can tell about other planets, other asteroids, everything. But over the long period of time, I mean that span of time is millions of years. Okay, which no one could predict what would happen after million of years. But after million of years, unpredictable things can happen. That is, that Earth won't be revolving in its own orbit. Okay, and other planets won't be revolving in their own orbits. Things will get chaotic. Okay, like the pendulum you saw. Initially, they started very close to each other, but afterwards they started to drift apart. So the motion of planets will be behaving like that, and it is already been proved. Okay, so solar system is chaotic. But for now, for nearby time, which is 1 2 years, 30 40 years, 100 years, you are feeling that is the time is very less actually. The 100 year time is very less. Actually, it is chaotic in the time scale of a million of years. Okay, after a million of years, you can see that they won't be revolving around in their own orbit, and we won't be there to see it also. Okay, anyway, so let's start. So, motivations, we learned a lot of things. So this all things fall under a common branch known as a dynamical system. So dynamical system. So what is a dynamical system? So dynamical system is a system in which things or variables change over time according to a given rule or a set of rules. There can be one rule or there can be multiple rules. So a system which systems which over time, evolves over time according to a given set of rules. Okay. Can you give me an example? Yes. Like you can say like a pendulum. So this is a pendulum. Okay. So the pendulum is a good example of a dynamical system. Why? Because this is a time t equal to 0 and you hit a push. Then the pendulum goes and it comes back and slowly reduces here. Okay. So the motion of the pendulum is already known. Okay. Can you predict what is the velocity of the pendulum at time t equal to 3 seconds? Yes, you can always predict. Okay. If you keep it in vacuum, all those things like ideal conditions, you can write the set of differential equations. You can even compute the time period of the pendulum. What is the time period? Yes, something like that, if I remember it correctly. Okay. Anyway, so time period of a pendulum is something like this. It depends on the length of the pendulum. Okay, the more the length of the pendulum, the time period is less. Okay, little the pendulum is, the time period is more. Okay, so through this you can predict everything. It is a deterministic system. It is a totally deterministic system, means you can determine everything about it. But this is a good example of a dynamical system. Okay, pendulum. Why pendulum is a good example of a dynamical system? Because the state of the pendulum, that is the state x, the distance and the velocity of the pendulum, changes with respect to time according to a given rule, according to a given set of differential equations. Yes. So therefore, pendulum is a good example. Motion of a pendulum is a good example of a dynamical system. Motion of a pendulum is a good example of a dynamical system. Right? Can you give me similar examples of a dynamical system? Wind. Wind changes over time. Okay. I was sitting in my office today and I realized, I was preparing for this class and I realized that wind is actually a dynamical system. Because last week here, There was no wind. There was only sunny. It was totally sunny. Now over 2 3 days it has started raining. Yes, and now today is very windy. Today is very windy. Yes. So what had happened is I had two doors, and the door, one of my colleagues' door, is continuously opening and slashing, opening slashing. Okay, that means the wind is going and the wind is again bringing it back. Okay, it is following a periodic pattern. Okay, so continuously the same periodic sound was there, right? So wind is also a dynamical system because wind changes over time. Wind changes its direction over time. So wind is a dynamical system. Can you give me another example? Weather. Weather is also an example of a dynamical system because weather doesn't stay the same. Weather changes over the period of time. Last 2 days it was sunny because of some dynamical variables of humidity and all those things. But today it is windy. Yesterday it was rainy. Yes. So weather is changing with respect to time, and hence weather is a dynamical system. Okay, fine. Any other things? Your age. Age is also a dynamical system. Age is changing every year by one. Okay, fine. Age is a dynamical system. Any other things? Your life. Life is also a dynamical system. Okay, because life doesn't stay the same. Life changes. So life changes with respect to time. Life changes over the years. So life is a dynamical system as well. But there is no rule of life. In dynamical systems, you can have a rule. You might not have a rule, or no one has decoded the rule. Okay, life, we don't know if it follows according to the rule, but for everyone life is different. Fine. Any other example? Is this a dynamical system? Your footsteps today. Your footsteps today. Yes, it's a dynamical system. The footsteps you took yesterday is very different from the footsteps you took today. Yes, maybe today no, not much friends are there because it's a Friday, and so you don't have to go to other rooms or other chambers, anything like that. But Monday, Thursday, and all, like, friends are here, so walking increases. Okay, so you can check your if you are using an app, pedometer or something, you can check your number of steps a day, and you can observe the trend, how many steps you have walked over the days. So that's a dynamical system because number of steps per day is changing over time. Okay. Fine. Lot of examples. The same way you saw the double pendulum, which is like this double pendulum, it is completely chaotic. Okay, because you cannot predict. Cannot predict. Chaotic means cannot predict, right? Yes. So double pendulum is chaotic. What does it mean? It is like if you just change the initial condition, then they were separating out totally. Yes, you cannot predict where one will go, right? Same happens with weather. Weather is also a chaotic system. You cannot predict weather for more than 2 weeks. Weather is highly unpredictable for more than 2 weeks. Therefore, you see every day in the news, they predict the weather today, tomorrow, maybe. Hardly within a week. But nowhere you have seen that they say that after 2 weeks this will happen. Of course, there is a prediction that if somewhere in some country of Vietnam some flood is occurring, then it is okay to say that in India also it might come due to the winds and all. But through simulations, they cannot predict. Why they cannot predict? Because weather system is chaotic. Weather system is also chaotic. Means tiny change in your decimal numbers will result in huge loss, huge errors in your outcome. If you challenge me that yeah, why can't we predict so accurately in the age of AI and machine learning, then I would say that however we advance, we can never eliminate it. Because I said that in the previous class that when you are in high school days or school days, you take your scale and measure 3 centimeter. So 3 centimeter in your scale, draw a line segment of 3 centimeter. So you mark 2 points, start from 0, take a point at 3, and take a sharp pencil and draw a line. So my question is it exactly 3 centimeter? Those who are absent in the last class, how many of you think that it is exactly 3 centimeter? why, how much you try, it cannot be exactly 3 centimeter, because there is a width of your pencil nib. Yes, so that due to that width of the pencil nib, it will be always less than 3 centimeter. Yes, always less than 3 centimeter. Can you achieve exactly 3 centimeter using a robot also? Cannot. How precision you do? Cannot. Even you make a nib of nanometer, still the error will be of 10 to the power minus 9. Okay, but the error will be there. The error will be there. You cannot eliminate that error to zero. However you do, so error will error will always be there. But due to that error, due to that as tiny error, chaos occurs. Due to the tiny error, a small change in initial condition leads to huge outcome. Okay, so this is what is chaotic. Fine. So let us go to the new thing, that is dynamical systems. Now you know what is a dynamical system. Dynamical systems are of two types. So dynamical systems are of two types. So one is known as flows, another one is known as maps. Flows are usually modeled by a system of differential equations. Okay. Whereas maps are modeled by recurrence relations or equations. So what does it mean by that? So flows are modeled by set of differential equations. They are of this form, that is, say x is a variable, state variable. Anything which changes over time is known as a state variable. So here dx by dt means x is changing with respect to time continuously. So x here is a state variable. So dx by dt, so how it changes, how variable x changes with respect to time, right? So there is a rule. So maybe 3x square, or maybe you can add a cos x to make it more complicated. Fine. So the dimension of this system is one dimensional. Okay. Similarly, you can have two dimensional systems. Like you can add a plus y square here and add 3x cube plus 5y cube x. So this is a two-dimensional system, two-dimensional coupled system. Why? Because x, the rate of change of x depend on both x and y, and the rate of change of y also depends on both x and y. So x and y are coupled to each other. Due to change in y, x is affected. Due to change in x, y is affected. So it's a coupled system of flows. Okay. So therefore, when you add a z part also, it gets interesting. That is 3z cube plus 5x square plus y square something. Okay. And those who have the paper where they are studying Lorentz system, Rosler attractors and all, they are these 3D systems. Okay. They are these 3D systems, nothing more. So this is one part. Let us come to maps. Okay, maps. What are maps? Maps means they are modeled by recurrence relations. Anyone you know about recurrence relations? Yeah. So how can we generalize it? Can we generalize exactly? But yes, it is like this. Xn plus 1 is some f of xn. Yes. Xn plus 1 is f of xn. So x is again a state variable. Xn is a state variable. Changing with respect to the iteration n. Changing with respect to the iteration n. Okay. So xn plus 1 is f of xn. Fine. So this is the idea which is known as a map. Okay. So today we will discuss one simple map. Okay. The class will discuss a simple map where you see in live that chaotic motion can occur in such a simple map. Fine. I hope that you appreciate it. Like that's the simplest example where you can see chaos. Okay. Fine. So xn plus 1 is f of xn. That means at n equal to 0, put n equal to 0, what you get? x1 is equal to f of x naught, right? So you have a point x naught, you apply the map f, you go to x1. Yes, what is x2? F of x1. Yes, so you apply f to x1 and you go to x2. What is x3? x3 equal f of x2. Yes, so you apply f again, you go to x3. Yes, so what is our aim here? In a dynamical, if you want to understand a dynamical system, we want to understand the long-term behavior of the system. That means what happens to xn? What happens? Xn tends to where? Is n tends to infinity. So as you increase n, what is going to happen to xn? What all things can happen? Can you tell? There are various possibilities. It can stay there itself. It can stay there itself, isn't it? Do you think it is possible? It can stay there. Or else it can go to infinity. It can go to minus infinity. Yes. Or can any other thing happen? Hmm? Yes. Yes, exactly. And Adhinson told the core of the subject actually today. It can oscillate. It can oscillate. Oscillate means in a more general way, it can periodically oscillate. Like A to B, then again B to A. A to B, B to A. Or A to B to C, then C to A again. Okay, periodically it can do things. Okay, we will take, so the fact he told is the one most difficult to find an example in real life, but we can find it in simulations. Okay, fine, that's fine. Can you give me one example where it always settles there? I mean, always stays there. It might not stay there over after a long period of time, can stay there whatever you do. Tell. Oh yeah, exactly. Xn plus 1 is equal to 1 or 1.5. So what is x naught? What x naught is not 1.5. X naught is up to you. X naught suppose was 0.1. Even if you take x naught to be 0.1, what is x1? What is x1? Yes, 1.5. What is x2? 1.5. x3 1.5. x 10,000 1.5. So it still stays there. It still stays there, right? Can you give me another example? Let us take xn plus 1 is equal to maybe 1 by n. Xn plus 1 is 1 by n. So what is, suppose you started with 0.1, doesn't matter. What is x1? X1 is not defined. Maybe I can do n plus 1 so that it is well defined. Okay. Okay. What is x1? 1. What is x2? X2 is, yes. What is x3? Yeah. So what is x? 10,000? 1 by 1, 1 by 10,000. Yes. So as n tends to infinity, where the variable goes? 0. Yes. So it is settling at 0. So again it is settling at 0. Okay. Good example. Any other example we can take? Let us take xn plus 1 is say 5xn. xn plus 1 is equal to 5xn. Can you start? Let us put n equal to 0 as usual. What is, so what you get, x1 is equal to 5x naught. Yes. Can you tell me any x naught we can take? Up to you. It's known as an initial condition. X naught is known as an initial condition. So can you tell me any x naught? Anyone? 1. Okay. What is x1? What is x2? 25. x3? x4? 16. x5? I see 3125. Is it? No. Huh? 3125. Correct? Correct or wrong? Yes, correct. This is common aptitude. It should run, your brain should run like a horse. How you can do this? 625 you split into 6 and 25 and multiply by 5. This is 3000. 25 into 125. 3125. Finish. Brain should work like horse, cannot sleep like this. Okay, fine. So what is xn as n tends to infinity? Can you tell where xn is going to as n tends to infinity? You can see 1, 5, 25, 125, 625, 3125. It is increasing rapidly. So where xn will go as n tends to infinity? Anyone? Yes, it will go to infinity. So it diverges. So this is a good example of a system where it diverges. Yes, fine. Let us come to Adhyanson's case. Okay, oscillating. Can you give me an example where it can oscillate? Hmm? Sin n. Yeah. You could have given a better example than this. Okay, you can play with this. Okay, I will play with another one. Xn plus 1 is say minus 1 to the power n. N plus 1, fine. Fine with me. Or minus 1 to the power n, also fine with me. Can you tell me x not equal to 0.1 suppose? So what is x1? X1 is 1. X2 is minus 1. X3 is 1. X4 is, yes. So isn't it oscillating? It is oscillating in between minus 1 and 1. So it's a period 2 orbit. It's a periodic orbit. It's a period 2 orbit. What is a period 2 orbit? You oscillate, it is a period 2. That means first 1, then minus 1, then again if you iterate, it will go to 1. It's a period 2 orbit. Okay. So this guy which you saw here, it was going to 0. That is known as a fixed point. That will read more detail. What is a fixed point? What is a periodic point? All those things. Fine. So good. So this is actually, this example we took is is an example of a linear map, because xn plus 1 depends on the past value xn linearly. 5xn is a linear function. So this is a linear map. Okay. Now you can take a nonlinear map. That is xn plus 1 is equal to 5xn square. If you take this example also, will it diverge? It will diverge. So xn tends to infinity as n tends to infinity also. But something amazing happens, something really amazing happens if you write this system in a different way. That means xn plus 1 is some r into xn into 1 minus xn. So this is just like r into xn minus r xn squared. Yes. See, it is very simple map. It is a very simple map. How it is simple? It has a linear component and it has a quadratic component. Yes. But this map was first devised by Robert May, who was a biologist, mostly population dynamics person, who gave a population model. Mostly ecology people know about this. Mostly the students who are studying ecology here, MSc ecology. If you ask this model, they will say, yes, I know about it. Okay. So this is devised by Robert May, and it is a well-known map known as logistic map. And it's a one-dimensional map. Okay. So it's a one-dimensional logistic map. Fine. Okay. So the idea is xn plus 1 is r xn into 1 minus xn. Can you can always do by hand, but believe me, it will be terrible. It will be terrible if you do by hand, really. Why? We will see computationally, and this is where computational nonlinear dynamics begins. Okay. You can study this by hand, but you cannot study this by hand. Okay. So what is our aim? So you took xn plus 1 is 5xn. You took xn plus 1 is equal to 5xn. You studied the dynamics. But here something more important is there. Xn plus 1 is equal to r into xn into 1 minus xn. So one can ask the question, how the dynamics of x varies as I vary the parameter r. As I vary a parameter. This is known as a parameter, like control parameter. It is up to you which one to take. Okay. As I vary parameter r, it's like a remote control of AC. Like you can decrease the temperature. So temperature is a control parameter. You can decrease or increase the temperature. So same way you can decrease or increase R. Okay. So therefore we don't say decrease or increase. We say vary. The generalized word is vary. We say vary the parameter. Yes. So as I vary the parameter R, how the dynamics or how state variable, this X is a state variable, as I mentioned, state variable X evolves. Is this a valid question? What do you think? Is this a valid question? I mean, previously it was 5, but you can generalize this. Why 5 is only the best one? I can take it 2.5, I can take it 3. So I generalized it like xn plus 1 is r xn into 1 minus xn. So the question is, as I vary the parameter r, how the dynamics of x changes. Okay, how we can understand it? That is my question. Okay, fine. So yeah, can you think of it? Can you think of it? How it changes? Any ideas? Okay, okay, fine. So what we can do? I mean, here your brain should start functioning. I mean, how we can analyze it? Treat it as a challenge, like how we can analyze it. Use all your data analytics concepts, everything, whatever you have learned so far in this course or courses before this. How you can use some ideas from there and visualize this dynamics. Of course, as I told you that we have to vary parameter r. That means I have to vary with something. That means it should be in one of the axes. It should be in one of the axes. Yes. Can it be in one of the axes? Yes, parameter r is in one of the axes. And what I can study, what I want to study, how x is changing. How x is changing as I vary parameter r. So x can be on the y-axis. Yes. Now what we have to do? We have to vary r from one value to another value. Can you give me a value? R can be from 0. R can be from 0. Okay, 0. Up to what you want to go? 5 or 10? Anything? 5. Okay, maybe 5. We can analyze. Okay, now comes the question. From 0 to 5, you want to vary. This is the coding aspect I am talking about. We want to code it up. After this, I will show you the code and the result. But I am telling you how to code this without showing you the code. Okay, I am telling you the pseudo code or something like that. So from 0 to 5, I want to do linspace, a range. A range. What should be spacing? What spacing you want? Point 0.1. Okay. So after this 0.1, 0.2, 0.3, so on, 4.9, then 5. Yes. So for each of these values you have mentioned, what you have to do? For this value of r, what you have to do? You have to iterate the map. So xn plus 1 is equal to 0.1 into xn into 1 minus xn. Yes. Agree? 0.1 into xn into 1 minus xn. Fine. So what you have to do? You have to iterate the map. You have to iterate the map. Like to start with some initial condition 0.1, what should be x1? It is difficult to calculate, right? It's difficult to calculate. And therefore we have to code this up. That's the motivation to code this up. Can you tell me? You are sure what is this? 0.1 into 0.1 into 0.9. What is this? This one? Is it correct? Or there will be 1 0? Yes. Fine. Agree. Agree. What should be x2? Difficult, right? So x2 should be 0.1 into. Yeah, you write that. Yeah. Okay. So it's difficult. Okay, we understood it's difficult. Okay. So what we will do is we will plot those points. We will plot those points here. Whatever this value 0.009 we'll put a dot. X2 we will put a dot. X3 will put a dot. Dot 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 dot. Yes. So for then your looping will come to r equal to 0.2. It will put the dots. Again, till you do this job in a for loop, you use a for loop. First it will do in 0.1, then it will do in 0.2, so on till 4.9 and then 5. So you will get a huge mesh, isn't it? You will get a huge mesh. Agree? You will get some mesh. Can you predict how this mesh will be looking like? I mean, just can you draw in your notebook and show it to me like this? Like how this mesh will look like. Just 1 minute, we'll take a break and then I will show you the mesh, how it really looks like. Okay, let us see this logistic map. Okay, let us see this logistic map in coding. Okay, so what I did is, this is the logistic map r into x1 minus x. I have taken r to be 3.8. Okay, some parameter. Okay, some parameter. X naught is 0.8, just some initial condition. Then I am trying to iterate it. You can see for n iterations. What is n iteration? 100. You can actually do 10,000, 20,000, up to you. But for time's sake, I have done 100. So then I'm plotting x with respect to the iteration. Okay, the star, and I'm connecting those stars by a blue line. Okay. So you can see this is the time series plot. So this is the time series plot of the logistic map. It is not that simple as you think. As many people have predicted that it would converge to 0, might see here for this specific value that it is not going to 0. Is it going to 0? No. Is it like behaving periodically or cyclically? No. Can you predict what will happen in the next step? Is it repeating itself? No. It is not repeating itself. Okay, fine. Now we started with a small initial guess, that is 0.8, right? Here we started with 0.8. Now I want you to show the same exact case we saw in the double pendulum video. Okay, we started with tiny change in initial condition and the outcomes were totally different. Here also we will start with tiny change, two different time series. I will plot two different time series overlaid on one another, one in blue, one in red. Okay, with tiny change in initial condition, and we will see whether the time series remains the same or not. What is your prediction? Will it stay the same? We'll check. So you see this one, what I have done. Can you see? I have taken two different initial guess. That is, one is 0.8, one is 0.8. How many zeros are there? 4 zeros and 1. So you can see there is a 0.00001 difference only in the initial conditions. Yes. Now for these two different initial conditions very nearby to each other, I want to plot the time series of the logistic map. Yes. How? And I will give it two different colors. One is blue, one is red. Can you tell me how the graph is going to look like? Will the blue and the red be on top of each other like same way? No. Okay. You'll see this. So you can see for 0.8 I am using blue, for 0.80001 I am using red. Yes. So you can see very nearby initial condition, they are starting here from here, n equal to 0. It corresponds to n equal to 0 here. And till time t equals to say 20, they are almost equal to each other. But after t equal to 20, something else happens. Completely something different happens. You can see blue is in its own way, red is in its own way. Blue and red are totally different time series, even though the parameter is same. See, the parameter is the same. Parameter is still 3.8, but these are two different initial conditions. Can you see some similarity between this graph and the double pendulum video? The double pendulum started with two nearby initial guesses, okay, and they were made to oscillate, and they were totally different from each other. So here the same thing is happening. Even though the initial condition is very same, nearby the same, two initial conditions, the long-term interval, long-term evolution of the system is totally different. That means red is not even overlapping with the blue. Okay, so in this case, if you take another time series 0.80002, still you will get a completely different time series from red and blue. Another third time series. Do you want to check? Maybe it can be yours, but I want to show you that even if you take a tiny time series, say 3, and run this code, it will still happen. Yes, you can see here. Okay, so the time series are totally different, and this is what I meant by chaotic. Okay, so it is highly sensitive to initial conditions. You started with a tiny change in initial condition, and it was so sensitive that the output totally changes. The red and blue is not matching. That way output is changing. So it is sensitive dependence to initial condition. A small change in initial condition can lead to a huge change in your output. And therefore this definition is known as a chaotic system. Fine. Now let us return to what we were planning. This I will tell you later. Okay. Fine. So you told that we'll start with parameter 0, right? 0 till 5, right? Or what? 5. What we are doing here, the same plot you did in your notebook. Okay, we are changing R from 0 to 0.5. Okay, maybe we have to keep it as what you call suspense. We will reveal it after the break. Okay, so let us continue with what we were discussing before. So what is the interval of R? What interval of R we are taking here? Yes, 0 to 5. And how many values of R I am taking in between of them? 10,000. Yes, 10,000. Yes, R min to R max, comma 10,000, length space. Yes, understood. Now for each values of those R, I will iterate our map. For how many steps? Can you tell? N iterations, 1,000 iterations. Yes. So let us run it. Okay. So let us see what kind of figure you are expecting. Okay, does it match with your notebook figures? What do you think? Will it match? Hmm? Let it run. It will take some time, of course, because you are running for 10,000 iteration and for each of those 10,000 values, you are running for again 1,000 iterations. So basically you are running it for 10 to the power 3 times, sorry, 10 to the power 4 times 10 to the power 3. So basically 10 to the power 7 computation time. Okay, the figure is ready. Yes. This is the figure. And has anyone expected this figure? This is the beauty of the system. Okay, so highly unpredictable. You cannot predict how it looks, but of course to understand this you have to code it up. This you cannot draw by hand also. Okay, now let me make you understand something more. You see at 0, at R equal to 0, what is the dynamics of the map? At R equal to 0, at R equal to 0, what is that value? 0. At R equal to 0, it is 0. Does it plot the point 0 at R equal to 0? Yes. So it is this point you can do because it is very easy. Yes. Now let us come to 1. At 1 also it is the same point. Okay. From 0 to 1, from 0 to 1, it will converge to 0, which someone was saying. So from 0 to 1, R value from 0 to 1, the value is 0. But when you go beyond 1, from R greater than 1 to R less than equal to 3, there is still a fixed point. Means your value is getting converged to a point. Yes. Then after that, when you cross 3, it starts to oscillate, which Adilson was saying. Like from this point to this point, then again this point to this point. 2 points it will oscillate. two times, period 2 orbit, period 2. Okay, it will oscillate in between 2 points. After that, what happens? It doubles. It doubles. Can you see 4 now? Can you see 4? 1, 2, 3, 4. Yes, 4. Now it will be a period 4 orbit. A, B, C, D. A, then to B, B to C, C to D. Then again, if you iterate D, it will come back to A. So it's a period 4 orbit. Yes. So again, it doubled to period 8. Yes. But after that is something very surprising. That is, you see a mesh. You see a black mesh. Yes. That is what is chaos. Highly unpredictable signal. You cannot predict the signals. Okay. Now let us see. Let us try to zoom the figure. Okay. Let us try to zoom the figure. Something more interesting is happening in between 3.5 to 4. Something interesting is happening on the x-axis if I zoom in from 3 to 4. So what I will do, I will just zoom in 3 to 4. Okay, 3.5 to 4. So what I have to do? I have to just change the interval. I have to just change the interval, right? Ready? Is it set? Yes. R min is 3.5, R max is 4. So it will be the zoomed version of that mesh. Okay. Let us run. We will see a very detailed and very complex structure which will again amaze you. Okay. Which will again amaze you. Okay. It has run. Fine. Let us go down. Yes. So can you see this structure? I don't think anyone would have means predicted this structure. It is out of prediction. Okay. How can you get this structure? Okay. It is highly complicated. But this part you can only see by using coding or using computation or simulation. Cannot judge it by just pen and paper. Okay. I mean, how many 1000 iteration can you do in pen and paper? Cannot do. Okay. So what you are seeing here, you see period is doubling 1, 2, 3, 4. Then again 1, 2, 3, 4, 5, 6, 7, 8. Period 8 orbit. Yes. And then it goes to 16 and then to chaos. The dark regions you are seeing, black stripes, are the regions of chaos. That means these are unpredictable signals. These are unpredictable signals. Unpredictable signal means if you start with different initial guesses, nearby initial guess, they will be highly unpredictable. That means highly sensitive to initial conditions. But are the periodic orbit highly sensitive in initial conditions? No. Periodic orbits are regular structures. Oscillations are regular structures. Even if you start with a nearby point, still it will converge to that periodic orbit. But the black stripe you see are the chaotic regions. Those are the chaotic unpredictable signals. Okay. So they exhibit sensitive dependence to initial conditions. Okay. Now we can play with this simulation. What we can do more, can you tell which part you want to zoom? I can zoom it for you. The more you zoom, similar kind of structure you will be seeing. Remember this structure. Remember this structure you are seeing. I will zoom in the next part and you will see a kind of a copy of this big part inside it. The more you zoom, the similar parts you will keep on seeing. So indirectly, it comes again a concept of fractal, which I think someone last semester gave some talk but is not here now. Yeah. So tell me some interval which you want to zoom in more. Any candidates? Which interval you want to zoom more? 3.9 to 3.9 to 4. Good. Okay. So let us see the figure again. So it is running. You can see how it is running here through this bar. It is looping around again and again. Okay, it is finished. Okay. So you gave a very big interval actually. So you can see that is full covered with chaos, full covered with chaotic signal. What is interesting is you could have given an interval 3.9 to 3.92. Can we do 3.9 to 3.92? Then again we will see similar kind of structure. Yes. I mean, yes. You are seeing some kind of similar structure, but we have to zoom in bit more. Can we zoom in between these two values? Just remember, let me know. 3.9050907. Yeah, you can see. However, it is a bit compressed from the vertical. I mean, not that intuitive. Why? Because see, it is a period 4 orbit. 1, 2, 3, 4. Then it is doubling here, which you are not able to see actually. Which you are not able to see. But it is a period 8 orbit here. 1, 2, 3, 4, 5, 6, 7, 8. Then it goes to chaos again. Okay. So similar kind of figures you can see for this logistic map. I mean, logistic map is such a simple quadratic map, one dimensional, but still it is exhibiting chaotic property, that is chaotic signals and highly unpredictable signals. So just with a simple mathematical function, you can apply these unpredictable signals in cyber security purpose. Like you can apply it for image encryption, you can apply it for. Why it is not charged? Where you kept? Okay, fine. So this is the concept of chaos for now to you. But we will be exploring this system a lot. We will be exploring this system a lot. Okay, let us come back to some theory. So this is the simplest. This is the simplest dynamical system you can read or you can exhibit where you can see chaos. Okay, simplest dynamical system where you can see chaos. Okay. Let us come back. This is a discrete map, right? This is a discrete map. Now, let us try to understand what we will be understanding in this course is we will be understanding what is a fixed point. Okay. What are periodic points? Chaos. Or chaotic attractor, you can say. A fixed point is also an attractor. Okay. A periodic point is also an attractor. Whenever you iterate your system and whenever it get converged to some orbit, that is an attractor. Whenever your iterates get converged to some signal, it is always an attractor because your system is getting attracted to that state. Okay. If it is not getting attracted to that, we call it a repeller. Okay. But repeller we won't be studying here, only attractors. So these are all attractors. Okay. Fixed point is an attractor. Okay. So what is a fixed point? I am telling you about fixed point, periodic point, but first of all, what is the definition of a fixed point? So fixed point. Fixed point is the, first of all, it is the simplest invariant set of the map. Okay, simplest invariant set. That means, can we find a point where results like suppose x naught goes to f of x naught, and if you apply f of x naught, it will go to f of x1, so on, right? F of this is sorry, this is x1, this is f of x1, this is x2, this is f of x2, this is x3. Yes, exactly. So what is our point? Even if we apply our map again and again, it will be at the same point. Can there be a point if you apply f to it, it will go back to the same point? This is known as a fixed point. Is there a point x star which you apply? This is a point x star which you apply the map f and it results to the same point back again. That means that is a fixed point. That means fixed. So that condition x star is said to be a fixed point of map f, that is xn plus 1 is equal to f of xn if x star is equal to f of x star. If x star is equal to f of x star. Okay. Now, my question is, did you understand this definition? That means you have a point x star. If you apply f to that, it is f of x star and it should be the same point again. So x star is equal to f of x star. Yes. So my question is, can you find fixed point for this logistic map? So for the logistic map, take logistic map. Take logistic map, for example, xn plus 1 is f of xn, that is equal to r times xn into 1 minus xn. Yes. Now we are interested in computing the fixed point. I think it is wrong to say the, okay. Computing a fixed point of logistic map. Why? Because it is the simplest invariant set. In order to understand the dynamics of the logistic map, we have to understand some of their key components like fixed point, periodic point, chaotic attractor, etc. So can you find fixed point for this system? So you have to just do x star is equal to f of x star. F of x star is equal to r into yes, r into x star into 1 minus x star. Yes. Can you solve this? It is a quadratic system. What you get? Can you solve? Tell me, what is x star? What is x star? Yes, is this equation you will get. So r x star square plus r x star square plus x star minus r x star equal to 0. So x star you can take common. So r x star plus 1 minus r, is it equal to 0? So x star can be 0 or x star can be, yes, agree? So therefore, is it correct? How will you know if it is correct? Is it correct? I hope you write it down in your notebook. We'll go to our simulation. Let us go to our simulation. Yes. Go to our simulation and let us do from 0 to 5 again. Yeah. So can you see that from 0 to 1, the fixed point is 0. X star is 0. We have given x star can be 0 also. Yes. Now, from if r is greater than 1, then x star is equal to 0 is not a fixed point. R minus 1 by R is a fixed point. Now take any value, say 1.5 or maybe 1.5, let us take R equal to 1.5. So R minus 1 by R, what is the value? What is the value? 0.3333. 1 by 3. Yes, isn't it? At R equal to 1.5, what is the fixed point value x star? Put R equal to 1.5 in R minus 1 by R. What is the value you are getting? You have to be a bit more active. Then only you will be able to grasp the concept. What you are getting? 1 by 3. Yes, 1 by 3. 1 by 3 is around 0.3333, right? And you can see it is the same point here. It is lying in between 0.2 to 0.4. So you can see it is 0.3. So whatever you are computing and whatever you are seeing in simulation are matching, are going hand in hand. Okay. So that means definition of fixed point is quite correct. Yes. Okay. Now let us see at a very good example. R equal to 3. R equal to 3. At R equal to 3, you will have to get this fixed point. So at R equal to 3, what you will get? 3 minus 1 by 3. 2 by 3. 2 by 3 is around 0.66. So you can see here, yes, it is lying above 0.6. So you can see that whatever, and x star is equal to R minus 1 by R. X star is equal to 1 minus R minus 1 by R. So x star is equals to R minus 1 by R. That is equal to 1 minus 1 by R, right? So can you plot this function with respect to R? How it will look? Plot x star versus R. Can you do? What you will get? See how to exercise your brain in this case. X star, if suppose x star is equal to 1 by R, then x star is inversely proportional to R, right? As R increases, x star decreases. Yes. So therefore, this is like a hyperbola. X star R equal to 1. X star R equal to 1. It's a hyperbola. How it should look? X star R. It should look like this. Yes. As R increases, X star decreases. Exactly. Now what you are trying to study is not this. What you are trying to study is X star equals to 1 minus 1 by R. So as R increases, X star what happens? As R increases, X star what happens? Think. What? Opposite means? This was like this. X star if is equal to 1 by R, it is like this. So X star equal to 1 minus 1 by R. Close to 1. At R equal to 1, what happens? At R equal to 1, X star is 0. So this is 1 and it will start from here. Right? So take R equal to 2, what happens? 1 minus 1 by 2, that is 1 by 2. Right? So what happens somewhere here? 1 by 2. Yes. So it is increasing. So it is increasing. So it will be like this. Isn't it? Yeah. It can't go beyond 1. Because it is 1 minus something. So it can never be beyond 1. So it will be within 1. So as R increases, so what is the final value? That you don't know. Means that is not our concern actually. But we just want to understand the behavior, how it looks. So it will look like this. Not like this. It will look like this. It goes like this, right? Can you see that in the graph now? Here. Can you see this in the graph here? So now you understand. Now you understand why in the bifurcation diagram you are seeing the curve like this. Because x star is equal to r minus 1 by r. So as parameter r increases, x star depends on r. So it behaves like that hyperbola. Okay, reverse hyperbola. Okay. So something here something interesting is happening here. At around 3, something very interesting happens. Okay. That we will cover in the upcoming classes. Okay. It is a bifurcation actually. It's a doubling bifurcation, period doubling. 1 is getting double to 2. Do you see 2 is getting double to 4? Is 2 getting double to 4? Hmm? Yes. 2 is getting double to 4. 2, 1, 2, 3, 4. Is 4 getting double to 8? Yes. Is 8 getting double to 16? Yes. So it's a period doubling cascade. 1 is going to 2, 2 is going to 4, 4 is going to 8, 8 is going to 16, and so on. This period doubling route to cascade leads to chaos. This is one of the property. Okay, so these all things we will explore slowly one by one. No need to hurry, but today we explore this part. Why this part came, that we explore today. Yes, why you actually see this for a logistic map, why this behavior exists. So you saw this, okay? That's good. Fine. Maybe, okay. We understood sensitive dependence also. We understood sensitive dependence to initial conditions. Yes. So there is a question. This curiosity come from you, right? So you have x star and you are starting from x star plus delta, right? Yes. So just 0.0001 difference, isn't it? I mean, you need to understand why I need to take 0.0001. I can take 0.002, 0.0003. What happens if I take those? Okay. So this is the plot for that. Like this is the data, no need. So here I wanted to say that log 10 delta I have plotted. Okay, log 10 delta I have plotted. Delta means the differences between initial conditions, the difference between initial conditions, the log value. So if it is minus 1, what if log 10 delta is minus 1, what does it mean? It is delta is 10 to the power minus 1. The separation is 10 to the power minus 1. That means the values is like 0.1, 0.2. One initial condition is 0.1, another initial condition is 0.2. If log 10 delta is minus 2, what does it mean? Delta is 10 to the minus 2. Delta is 10 to the minus 2, right? Are you getting why delta is? Yes. So 10 to the minus 2 means how it should look like 0.1 and 0.1 and 0.11. So the difference is 0.01. Yes. Agree? So 10 to the minus 8. So you can see delta, let us take minus 8. The first value. So when you take minus 8, what happens? What is delta? 10 to the power minus 8. Delta is very close, extremely close to each other. I mean, two initial conditions are extremely close to each other. Agree? No? Not getting. Huh? Not getting. Okay. Okay. Yes. Okay, let us start with two. What I did is, these are the two initial conditions. See this. I am talking about this graph. What is the delta here? Can you tell me the value of delta here? Yes. What is delta here? Who will tell? Huh? 0.1. No. There are two initial conditions. One is blue, 0.8. The other is in red, 0.8 to 0.00003. These two effect of initial condition we are seeing, right? So what is the difference between those initial conditions? 0.00003, right? So that we are trying to understand what happens if I do 10 to the power minus 1 delta, 10 to the power minus 2 delta, 10 to the power minus 3, 10 to so on up to 10 to the power minus 8 delta. Yes. So how much time it takes to be different? That's what I am checking. Okay. So this is the plot for that. Okay. So you can see for when delta equals to 10 to the minus 1, then the iterations is very less. Means less number of iterations are needed to be separated out. But the moment they come extremely close to each other, it is very difficult to separate them out. Yes. How? How can you tell that? You go to the first point. Go to the first point. When it is minus 8. When log 10 delta is minus 8, what is delta? What is delta? Basic logarithm. 10 to the power minus 8. Log 10 is 1, right? Log 10 is 1, right? So log 10 to the power minus 1 is, this minus 1 will come here. Minus 1 log 10. This is minus 1. Right? So log 10 to the minus 8. Minus 8 will go here. So what happens? Minus 8 log 10. This is minus 8 times 1. Minus 8. It's basic things. This can come in aptitude. Definitely. Don't skip these basic things. Can come in aptitude. So when log 10 delta is minus 8, the iteration to separate is goes beyond 25. You can see here, it goes beyond 25 when it is very close to each other. So when the points, when the difference between initial condition is very less, it takes a lot of iterations to separate them. That's what this plot tells us. If they are bit away from each other, it takes a very less iteration. You can see 10 to a minus 1. The first iteration, it took less than 5 iterations. Y-axis is iterations. Okay. Hope you got the idea. Okay. So this is what I wanted to teach. Okay. Next class, we will see how Rx into 1 minus x looks like. Did you understand? Did anyone try to plot how Rx into 1 minus x looks like? So I want to know how Rx into 1 minus x looks like. Okay. So you can see how it looks like. It looks like one hump down parabola. Yes. You can see there is a one tip. One maximum is there. Can you find that maximum? Can you find that maximum where it reaches maximum? Optimization. So just to differentiate and put equal to 0. At what point it goes to f prime equal to 0 means it should have a parallel slope. Can you see that here it is a parallel slope? So where you see a parallel slope? At x equal to 0.5. So at x equal to 1 by 2 it has a maximum. Yes. So there is a speciality about this function. This kind of chaotic signals you see always there is a property, like if it is a hump, then you see this property. Okay. So fine. So this is one map. So let us vary R and see if something happens. Yes. So you can see when R is negative, it turns, the parabola turns. When R is positive and all, it and increasing, the hump increases. Okay, the hump increases. But one more thing, in your logistic map, can can it go to, can it go away from 1? Can the output xn plus 1 is equal to rxn into 1 minus xn? Can the value of xn go beyond 1? It can never go beyond 1. It will always lie in between 0 and 1. So you can see the y-axis. For the range 0 to 4 I have taken, the value of x has never went above 1. It has always lied in between 0 and 1. It always lied in between 0 and 1. Okay, fine. So these are some of the properties which not many people were aware of. So everyone has understood the aspect of logistic map from their point of view. Okay. So electronics person, what they did is they implemented logistic map in terms of electronic circuit. Okay. They made an electronic circuit of xn plus 1 is rxn into 1 minus xn. and varied the potentiometer and resistor values, okay, in the plot, and started to see the patterns. Okay, computer simulations, those who are doing, scientists or engineers, they started to use Fortran or many other softwares to visualize this, code it up, okay, plot the time series. Okay, so everyone has their own point of view, but this is a, so what is this figure? What is this figure? Can you tell? So this figure tells us what happens to the system, logistic map system, if you vary the parameter R. Yes. So this kind of diagram is known as a one parameter bifurcation diagram. Means we are trying to understand what happens to the variable X as the parameter R changes. Okay, only one parameter R changes. So such kind of bifurcation diagram therefore is known as one parameter bifurcation diagram. Means you are trying to understand the bifurcations occurring when one parameter changes. Okay, so what is a bifurcation? That we'll understand in few classes more. Okay, so hold on. So you will be visualizing these kind of things throughout the course. Okay, so we will be seeing, so nonlinear dynamics has a lot of beautiful figures, so you will be encountering this kind of figures throughout the course. So highly unintuitive figures, but yeah, maybe we will look into the logistic map. Okay, so whenever you take compositions of logistic map, the humps increase. Okay, so you can see the first composition is in blue, it is one hump. The first composition is just Rx into 1 minus x, that is just a reverse parabola. When you take two composition, it is in orange. How many humps you see? Two humps. Okay, two upper humps. Okay, so it is like two logistic maps are side by side. When you take three composition, you see a lot of humps. So this is the idea. So the more you increase the composition, the more humps you see. Okay, so that's the idea. Then next class we will discuss about another interesting aspect known as a cobweb. Okay, what is a cobweb? Fine, maybe let me see. Yeah, how a cobweb looks. We will be understanding this concept, how these bifurcation diagrams are all related. Yes, what is a bifurcation? What is a saddle node bifurcation? What is different kinds of bifurcation? We will analyze. So there is time. So I think we should stop here. Okay, so we collect the attendance. You and Durga can collect the attendance of today's class. Done. Many people are absent, is it?